Okay, welcome back. Happy Monday. We just handed back test number 2. The median grade on this test was 81.5. I'm happy with that. Some probably half of you are happy with that because you're over that number and half of you are under that number. So if you have individual questions about your test, you can see me after class. I'm happy to talk to you. I also handed back a bunch of projects late last week and didn't have an opportunity to say how well folks are doing on these projects. And I recognize that in order to do as well as you are doing, you are putting a bunch of time into the project. So I'm here to say good job. I see it and I appreciate it. And it's, yeah, I'm quite happy with the work that people are putting in on those projects. And I'm happy to see the grades that are coming out of them. Speaking of projects, we've got our last 2 math projects of the year that I handed out on the test, but if you don't have them, let me know, but I think everybody got them. One on data regression and one on rainbows. Those things are due November 28th and 30th, so right after we come back from Thanksgiving break is the due date for those 2. I've seen people who have made significant progress on one or the other of these already. So you do have a recommended timeline, but you already have all the tools to answer every question on both of these projects. So if you feel like getting ahead, do so, right? At any point you can work through and complete any of these 2 projects ahead of time. Today we're going to cover something called implicit functions, and I think that's it on the calendar. Questions on the calendar? Okay, so again, jumping to page 5 of the big packet. By the way, this is the last packet of the semester, so no more handouts aside from a final project. Okay, our daily summary. Today, we learned the technique of implicit differentiation used when the equation for a curve is not written in the explicit format, which is y equals some stuff with x's. Okay, as usual, make sure you take time to look over your test after class and ask me if you have questions, or ask your classmates, which I saw some of you just doing, or work with a peer tutor or somebody in the math studio. Don't just take it and shove it in the binder, never to be looked at again. Take a look, figure out what went right and figure out what went wrong, and see if you can respond to that heading forward in this class. The usual stuff about the projects, don't wait until the last minute to do them. Work on them a little bit all the time, and it is strongly encouraged that you work with each other. And we'll start here with number 4 in our demo, which says find an equation for the tangent line to the curve x plus 2 times the quantity x squared plus y squared squared minus 9x squared equals -5 at the point -1, 1. So certainly the most complex equation we have seen this semester. What's unusual about this relative to all the other equations we've been playing with? We don't have y on one side, right? Every other equation we talked about, y equals, y equals, y equals. But in this case, the y is buried inside of a complicated equation with lots of other x's. And that's the heart of what we're after today, is to be able to take derivatives when the x's and y's are all jumbled together. Okay, so the curve is called a conchoid of Nicomedes. There's the curve. What's unusual about that? Not a function. What else? It's got like these 2 sort of completely unrelated looking pieces, right? You got this like vertical asymptote here at x equals -2, and the one curve just kind of bows out, but then this other like oval looking thing that just seems completely independent, but it is one curve. It is all the points that satisfy that equation right there. Okay, but we've got the point -1, 1. Let's go ahead and put a dot at the point -1, 1. It's right about there. And despite how absurd this curve looks, does it have a tangent line at -1, 1? Sure. So don't even need a straight edge, but just roughly draw the tangent line going through the point -1, 1. What kind of a slope are we expecting? Positive or negative? For sure it's going to be negative. Do you think closer to like -10 or -1? So it's closer to -1, right? It's a little steeper than the 45-degree line, but not that much. Y-intercept, positive or negative? Negative, maybe just barely, right? It's not going to be -10. It might be -1 or -0.5 or something like that. So our task is to find the equation of that line. Okay, we know we're going to use y equals mx plus b, and we know a point. We've got to have 2 things: slope and a point. And the point is given to us. It's -1, 1. What we need is the slope, and that's the hard part of this problem. So what we're going to do is take a derivative of both sides of this equation. I'm going to squeeze this in because I don't feel like rewriting it, but just to show you the thing we are doing to both sides is in front of both sides, we are putting a d over dx, which means take a derivative of the left-hand side, take a derivative of the right-hand side, and those two derivatives had better be equal, right? Okay, we're going to work our way from right to left here because that's the easiest. The complicated stuff is at the far left here. So let's take a derivative on the right. What do we get? 0. And really put this thing way over here because there's going to be a lot of space that we're going to fill in with the derivative of the left. So the derivative of -5 is 0. So far, so good. Next up, derivative of -9x squared, -18x. Easy peasy. Next up, I see x plus 2, I'll highlight that in yellow, times x squared plus y squared squared in blue. What fundamental derivative rule? Product rule, right? That is our multiplication rule. So we're going to let the multiplication rule guide us. For me, normally, when I do the multiplication rule, I do first times derivative of the second. The derivative of the second is the scary, complicated part. I'm going to keep delaying on that, so I'm going to do it in the other order. Second times derivative of the first, plus, and then something else. All right, so second, we copy. X squared plus y squared squared times the derivative of the first. 1, right? Derivative of yellow is just 1. So again, product rule, that was second times derivative of the first, plus the first, so copy the yellow, times the derivative of the second. So now we're doing the derivative of blue. And I'm still not ready to deal with that y yet because I see some stuff squared, right? We know how to take a derivative of stuff squared. What comes down? It's the chain rule. What comes down? 2 comes down. What are we writing? The stuff, x squared plus y squared as it is. What's the new power? 1, which I won't write. And now times the derivative of the stuff. I will underline the stuff. It is right there. So in here, we're supposed to be putting the derivative of that stuff. Yeah? Okay, x squared plus y squared. Derivative of x squared is easy. 2x plus. Now finally we get to the only thing that's really new. The thing that's new for today. It's the derivative of y squared. Guesses?
I'd say 2y.
2y. Perfectly good guess. We got to write that. 2y. Right? Derivative of y squared 2y. Seems reasonable. Okay, it's correct, but it's not complete yet. In your mind, imagine that you had the ability to solve this original equation before we did any derivatives. If you could solve that equation for y, so it's y equals some crazy complicated mess with x's in it, okay? If I wanted to take a derivative of y squared, because that's what we just did. I said y squared, you said 2y. So if I had y squared, imagine instead of the y, we've got this complicated mess with all the x's in it, okay? So I've got all of this stuff here, complicated things with x's in it. And if I said take a derivative of that, what would you do? You bring the 2 down, you'd copy all the stuff, and then times the derivative of that stuff, right? So, you know, these two guys are the same. So you bring the 2 down, you bring the 2 down. You copy the stuff, copy the y. So 2y is correct for saying bring the 2 down and copy the stuff. But what have we not put in here yet? No, we got the stuff. The stuff is the y, but it's the derivative of the stuff. So right there, when it says times the derivative of the stuff, that's the times this ... with all the x's in it. Well, the symbol for the derivative of y is just dy dx. I'll highlight that in green. And so the takeaway from all of this is that you take your derivatives as usual, and you treat x's and y's normal. But anytime you take a derivative of something with y in it, you have to multiply by dy dx. Say it one more time. Anytime you take a derivative of something with a y in it, you have to multiply by dy dx, because that's the derivative of the stuff. It's just the chain rule, but the way that we write derivative of the stuff here is always going to be times dy dx. Okay, so that's it. That's the derivative of both sides. Now, oftentimes we like to get dy dx by itself, and if I just gave you like that equation, and I said take a derivative, you'd say, oh, no problem, dy dx equals 21x to the 6, right? And it's already done, dy dx equals. Well, we don't have a dy dx equals. Our dy dx is trapped inside of this mess. So we have to do some algebra to untrap that dy dx, trying to get the dy dx by itself. So I'll write that in English, and then we'll do the algebra. Solve for dy dx. Isolate the y squared in the beginning. Yeah, so what would be involved in isolating that y squared? So let's think about the algebra. So the negative 9x squared would move over by addition, right? The x plus 2 would come under by division. So right now we've got a quotient rule so far. And then how would you get this y squared by itself? How would you get it? We'd have to take the square root of both sides, which means a plus or minus. And you got a big old radical with a quotient inside. And then you could subtract the x squared over, and yes, the y squared would then be by itself. So you could get the y by itself in this case, but thinking about what the derivative would look like, actually, honestly, this derivative is far easier than the one that we would have to deal with if we got the y by itself. And in the activity, you'll see equations where it's not possible to get the y by itself. Yeah, good question. Okay, so we're going to do some algebra here. We're trying to isolate dy dx, solve for dy dx. So we're going to move the 18x over, it becomes positive. We're going to move the x squared plus y squared squared over, it becomes negative. Okay, so let's do those two things. Okay, so that was just adding and subtracting terms. Again, the goal is to isolate dy dx. So how are we going to move the x plus 2 to the other side? By doing what? Dividing, right? Because this is all multiplication. So we're going to divide both sides by x plus 2 and also 2 and also x squared plus y squared. All right? So all three of these factors are going underneath on the right-hand side. Let's do that. Okay, and then I think just 2 steps left. Solve for dy dx. Which term moves over first? 2x will come over by subtracting, and then the 2y by dividing. So I'm not going to rewrite everything because I'm lazy. Minus 2x here, and then divide both sides by 2y. And so that gets rid of both of these guys. So there's our answer. Y dx equals all of that gobbledygook. So what is different about this derivative than all the ones we've done so far this semester? It's got y's in it, right? Normally our derivatives just have x's in it. Okay, so that was a luxury that we didn't appreciate until now, but when x's and y's are jumbled in the beginning, they're almost certainly going to be jumbled when you take a derivative. So this is the new normal. Okay, so this is the derivative at any point on that crazy curve. We wanted the derivative where? You need to give me both x and the y at -1, 1. And we need to know the y because there's y's trapped in here. So all we're going to do now is plug -1 and 1 in for x and y. So I think this is how we symbolize that. dy dx evaluated at -1, 1. Okay, so we're going to try not to write too much stuff here. 18 times what number? 18 times -1, so that's a -18, minus, what's in the parentheses? 1 plus 1 is 2 in the parentheses, right? Square them both and add them up. 2 squared becomes 4. So I've got -18 minus 4. Divide by, how much is in the next parentheses? That's a +1, right? -1 plus 2, so I got a 1 there. Times there's a 2 floating, and then how much is in the other parentheses? It's 2 again. And now we're at the purple. Minus 2x becomes what? Plus 2. Divide by, and now the green is a 2y. So that's a 2. Everybody see where all the pieces came from? It's just plugging in x and y, -1 and 1. Okay, let's clean this up. -18 minus 4, that's a -22 on top of a 4, plus 2 over 2. Reduce that guy, -11 halves, plus 2 over 2. This guy right here can get a common denominator and become 4 halves. So what do we have on top when we add the fractions? -7 halves, and then that's divided by 2. -7 over 4. And that right there is the derivative at the point -1, 1. So what does it have to do with what you drew on that curve? That is the slope of that line. Is it reasonable? Negative? Not too big. Reasonable. Okay, that's just the slope of the tangent line, but this one said find the equation of the tangent line, so we just have a tiny bit left to do. So we'll do our y equals mx plus b. How much is y at the point? 1, so we go 1 equals, how much is the m? Times the x is -1, how much is the b? That's what we're going to solve for, so we'll put that there. Okay, so this becomes 1 equals +7/4 plus b. And then subtract 7/4. So we get b is -3/4. Is that reasonable based on the thing you drew on that curve? Y-intercept of -3/4? Yeah, that seems good. So then the final answer to this problem is y equals -7/4 x minus 3/4. Questions on the process? Okay, so the next page has our little summaries. Let's take a quick look. Number 6, if you have an equation that you cannot solve explicitly for y, then we say the equation defines y implicitly, and the technique we used above is called implicit differentiation. How do we know we need to use this technique? The equation has the x's and y's all jumbled together. That's the giveaway. So number 7 is the bullet point summary of here's the only thing new today is when differentiating implicitly with the x's and y's all mixed up. Just remember, whenever you are taking a derivative of a term with a y in it, you take your derivative as usual, but you multiply your derivative by dy dx. That's representing the derivative of the stuff from the chain rule. Okay, it's the only thing that's new. Normal derivatives for x, normal derivatives for y, but after you take any normal derivative with a y in it, multiply by dy dx. Okay, so before you jump to the activities, I think this is a good time for us to spend maybe 2 minutes just playing around with something called sliders on GeoGebra. Going back to this equation right here. So we had this like crazy curve, right? It looks like two different things that have nothing to do with each other. Let's just explore a little bit. This x plus 2 up here, we're going to generalize. I'm going to call that x plus a. And then x squared plus y squared squared, I'm going to keep that as it is, minus, and then over here, instead of a minus 9, I'm going to call that a b, just to see what happens if it's not 9, but maybe it's 8 or 7 or 10. And then over here equals negative 5, I'm just going to call that c, okay? And so we're going to talk later this semester about families of curves, and that's what this is. We've got 3 different constants, a, b, and c, and by changing the constants, you change the graph, right? And so typically, you know, historically, it's been really challenging to think about the behavior of complicated things like this, but with technology that we have today, it actually becomes really easy. Here's what we're going to do. We're going to click on this slider tool in GeoGebra and just click in the blank space someplace, and it says, okay, here's a slider called A, and it's going to range from -5 to 5. And so if I just take this point and I drag it to the far right, it's 5, and at the far left, it's -5, and lots of numbers in between, okay? All right, how much is a in the original equation? It was positive 2, right? Everybody see that? So a is equal to 2. So let's just set it to 2, and then we'll play around with it later. Okay, and then the next thing we're going to do is just click on slider again, and then anywhere in the blank space B, I'm going to let this guy go from -10 to 10. And B originally was this -9 here, all right? So we're just going to set this guy to -9. That's good. All right, and then the last one we'll have is a C. -5 to 5 is fine. So what we're going to do is we're going to type in the equation, x plus, but instead of x plus 2, what are we calling it here generally? A. You can just type in A. GeoGebra knows it's A. Times x squared plus y squared squared. And then it was plus b, was that an x or an x squared? bx? No, squared, wasn't it? Yeah. Equals, and it was a -5. I forgot. This guy was a -5. Was a negative. -5 equals c instead of equals -5. What do we do wrong here, gang? Bx squared. All right, I think it didn't like something that I did originally. Let's try it there. Okay. All right, so how does that look? Familiar, right? Like crazy, but familiar. I mean, okay, so let's see what happens. If we change this a, which is currently at 2, let's see what happens when we make a bigger. So apparently at 2.75, we don't have any part of that little oval thing left over. It just vanishes from existence. And then, oh, there, right? So again, like, yeah, I mean, this is something that like has changed over the course of my career, is that when I was a student, there's no chance we probably couldn't have even graphed a single one of these, like just one. Forget about seeing this, you know, this beautiful continuous behavior. And now it's just easy. It's really, really easy. What's going to happen on this side? When they touch, what's going to happen? They're going to merge. You guys remember them like unmerging over here, right? Like we've seen it over here, what happens. So let's see what happens on this side. There we go.
It's like a lava lamp.
That's right.
It is kind of exactly a lava lamp.
Okay, so that's the effect of changing A. Here's B, which is the guy touching the x squared, a -9x squared. All right, so come on. Nope, this guy. Okay, so so B, you know, like it's moving the line a little bit. We lost our oval type thing there. Yeah, and somehow B is boring. So the equations that we're going to play around with today, I don't have any practical applications for. Sorry. Sorry. But come on, this is cool to look at, isn't it? Look at that. Come on, that's awesome. Making a better lava lamp. That's right. All right, good. And so we had our starting values of A, B, and C, and then we just changed one of them. But we haven't seen effects of like changing two at a time. And we're not really going to play around. But for example, like if I just say, okay, I'm going to start with my A at -1 instead, and now change B. Oh, Jesse, is B still boring? All right, B's got something going on now. And so, like we're just looking at a small sliver of, like what's happening here. It's like, why? Why does that thing just disappear? Yeah, I mean, like it's really complicated, but the fact that we have this to visualize is still mind-blowing to me, is how easy it is to just look at these families of things. So we'll talk about families of curves later on this semester, but if you are ever interested in exploring curves, GeoGebra, or anything else with a slider, I'm sure Desmos has a slider, Mathematica, does Mathematica have sliders? Yeah, so like anything with a slider really, really opens up possibilities that we didn't have, say, 10 years ago. Okay, so the activities start on the next page. Let's see if we can get through them all.